Let's start in another 2 minutes, just in case someone else wants to join in. All right, I think we can begin. It's 7:04. Okay, so welcome. Good evening. I hope you've had a good day so far. This lecture and the upcoming 2 lectures, that is tomorrow and the day after, are a part of the Solstice Summer Project that's happening in Nakshatra right now. These lectures are intended to serve basic purposes or basic understanding of groups and symmetries for the people working in the neutrino project. But I feel this is also a generalized topic that every physics person sort of has to get an idea about. So let's get started. The talk is titled An Introduction to Groups for Physicists, because there's a difference between perspectives of how groups are viewed from a physics person and a math person. This lecture particularly will be a little math-based, more specifically a little bit of linear algebra and a bit of abstract mathematics. But I will try my level best to bring it to you in a way that everyone can understand, even if you're a 12th grader or if you're a master's student or somewhere in between of that. You can contact me at my email address if you have any questions after the talk. One kind request that I'd like to make is please do put your questions in the chat box today instead of unmuting in between the talk. Because I would like to maintain a flow during this talk. So yeah, please do put your questions in the chat box and I will answer them at the end of the talk. Thank you very much. All right, so let's get started. These are the things that we'll try to cover today. We'll have a look at matrices, and then we'll do a little bit of group theory, and then we'll combine those two to form groups of matrices. And then we'll look at a few specific groups called the orthogonal groups, the unitary groups, and then we'll see how they're applied in quantum mechanics, the unitary groups. And then we'll sort of try to understand what happens when you multiply 2 groups, the product of 2 groups. And we look at a specific connection, which becomes more useful when you're studying the standard model of particle physics. All right, so the first thing we're going to do is we're going to talk about we're going to talk about matrices. This is something that everyone is already familiar with. Right. So a matrix is just an arrangement of numbers as shown here in the box. I hope you can see that drawing. Right. So it's just a rectangular arrangement of numbers where you have m rows. So these are called rows and these are called columns. Right. And so this is a matrix, and we call this a matrix of order m cross n, m rows and n columns and so on. Each element of this matrix is represented as aij, where I represents the rows and j for the columns. All right. And if m equal to n, you have number of rows equal to the number of columns, then obviously it's a square in shape, and so you call them the square matrix. And any two matrices A plus B satisfy the commutative addition law. A plus B equals B plus A. That's fairly simple. They also satisfy certain properties of scalar multiplication, where if you are to multiply a number with a matrix, then every element of that number is going to be multiplied with the same same quantity that you are multiplying, the scalar. It's called the scalar. And this scalar can be a complex number as well, which means it can be of the form A plus IB, where I is equal to the square root of -1. It can be of any form that you like. You can also take a transpose where you exchange the rows and the columns. One of the most useful applications of matrices or matrix algebra and so on, or linear algebra, if you want to say, is solving linear equations. So these are systems that you've already seen, something like x plus y plus z equals a, and then you have, let's say, some other 2x plus y plus 3z equals b, and let's say x plus 3y plus z equals c. This system of equations can be solved using matrices. I won't be getting into that. And another application of matrices is to understand linear transformations. It's when you transform your vectors or your coordinate space, you try to transform your entire space into something else. Linear transformations are understood using matrices. And then now we'll look at a few types of matrices. We have a diagonal matrix where every other element except the principal diagonal, which is this, is 0. Then we have an identity matrix. It's just a diagonal matrix with all the diagonal elements equal to 1. And why is this important is because if you multiply any matrix with this, or if you do this, you get back your original matrix. It's pretty much like you're multiplying 1 with any number. Right? You multiply 1 with any number, you get back your original number back. There are also symmetric matrices and skew symmetric matrices. It's just where if you exchange the rows and the columns, you get back either the same matrix, then it's a symmetric one, or if you get the negative, then it's a skew symmetric one. All right. This whole idea of transposing and everything can be extended to the complex domain, and there we call Hermitian. There we call them to be Hermitian in nature, where the operator Hermitian is the dagger here, that is on the top. And the dagger here represents complex conjugation and transpose. So if you have a matrix with complex numbers inside it, taking the Hermitian of that would imply that you're doing a transpose of that and then taking the complex conjugate of every single element inside of it. And if they're equal, then you call that matrix to be Hermitian. And this is vitally important in quantum mechanics because every operator, if you're familiar with quantum mechanics, is Hermitian in nature. The next is an orthogonal matrix. We'll come back to these in terms of groups, but they're just sort of rotational matrices. You apply this matrix to some vector, it ends up rotating it in some way. And again, if you try to bring that to the complex domain, the orthogonal equivalent is unitary in the complex space. And the operation there is the Hermitian adjoint again, like we saw before. Okay. Right. Using matrices, we can also represent vectors from linear. I won't be getting into the details of all of this, but you can just represent any vector using the Dirac notation. This is called the ket vector from the Dirac notation. All right. And you can represent that as a column vector. And the advantage of using matrices as your vectors is you can extend your whole space into n dimensions. So you're already familiar with I vector being 1, you can write the I vector as 1, 0, 0 in 3D space, but you can extend it to any number of dimensions by just adding more zeros. So it becomes an equivalent of that. And you can also define a dual for this, something like a complementary for that, called the bra vector, again from the Dirac notation, which is represented as this. Now, why we need all of that is to preserve something called the inner product or the scalar product. All of this you can study when if you are doing matrices, but this is not the point of this is not the concept of our lecture today. So I would be skipping on most of this, but this is sort of a generalization of dot product, which I'm sure everyone here is familiar with. Dot product generalized. Okay, and this is kind of the vector product or the cross product generalized. It's not exactly that, but it'll help you get an idea as to what exactly it is. And this is called an outer product. This is an inner product, which gives you a number. And you have an outer product, which gives you something else. Not a vector, but something else. Right? Now is the time we start getting into groups. And in order to understand what they are, we'll just see what the definition is. Yes, there is a lot of mathematics here, but let me tell it to you very simply. Right? Consider you have, an orange, a banana, and a mango in front of you. What you would call those is a group of fruits or a set of fruits, right? But if I had, let's say, an Alfonso mango, a Banganpalli mango, and all those different sort of mangoes all together, then I would call that a group of mangoes. Why? What's the difference here? Is in the first, the set of fruits, I had different kinds of elements, and all were different sort of a thing. But when I sort of brought it down to mangoes, one thing I'm sure of is all of them are mangoes. It's just that the types of mangoes are different, but in the end, they are still a mango. So this particular set of mangoes, the Alfonso, the Banganpalli, the Badami, and so on and so forth, that we would call not a set, but we would call that a group of mangoes. And the same thing when you try to get over to abstract mathematical definitions. You have a non-empty set, G, right here, and you have a binary operation. We just put it as a dot, or it can be a star, or it can be some delta, whatever you want it to be. It's just a symbol, right? If it satisfies certain relations, this is called the associativity, which I'm sure you're already familiar with, the associativity of the elements inside. So if I take two mangoes and then mix them, I get another mango, sort of a thing. And that there should exist an identity element such that, whatever element I take and multiply with it, I get back my element, something like 1 if it was multiplication, or 0 if it was addition. And another condition is that there must be an inverse of whatever element I take. So if I have A, then I have some B, which if I multiply, I get back my identity element. It's more like if we're looking at multiplication, then if I have 2, then its inverse would be 1 by 2, and that gives me the identity element 1. This is the E for multiplication. Similarly, if we were to look at addition, I'm going to write at the bottom here. If I had 2, then if I add it with -2, I get 0, which is E, the identity element for addition. So multiplication here is a binary operation, and addition here is also a binary operation. All right. Again, you can go ahead and define different types of groups. One which we are concerned about is called an abelian group. Why do we have to bother about it? Comes when we are discussing gauge theories, which would be the topic of the third lecture. But what abelian group is apart from all of these three conditions, the 1, the 2, the 3, it also satisfies this relation here, the commutative law of whatever the binary operation you've defined it on. And if A dot B equals B dot A, where dot is the defined binary operation, then that particular group is called an abelian group, named after the mathematician Abel. All right. So that's like a basic intro to groups. You can also go ahead and define different types of groups. The permutation group, also called the symmetry group. Matrix groups, this will be our main topic for today. We're going to be focusing on matrix groups. And then we'll also focus on the groups with separate algebraic structures, not in detail, but something called the Lie groups, named after the mathematician Lie. It's Lie, not Lie. That's something everyone tends to get confused with. It's called Lie. All right. These are the things that we'll be focusing upon. And let's get into what we said. We'll be getting into matrix groups. So let's get into that. It's fairly obvious, matrix groups. So as the name suggests, it's a group whose elements are matrices, as simple as that, right? If I have a group of mangoes, then it's a mango group. And if it's a group of matrices, then it's a matrix group. That's as simple as that. And why can we call it a group? One thing is we assume that matrix multiplication is associative. So let's go back here, and I'm going to erase a little bit of this so that it's a little clear. Right. So the first one was associative, right? And we assume that matrix multiplication is associative in itself. There is an identity element. We define the identity matrix. So there is an identity element. And the inverse, this is a little tricky. The inverse for a matrix, I'm going to write this in blue. Inverse of matrix, I hope it's visible. Yeah. Inverse of matrix exists if and only if the determinant of that matrix, if it's A, is not equal to 0. Right? So we call them non-singular. These are called the non-singular matrices. And right, so we consider a set of matrices that have non-zero determinant, which means their inverse exists. So these are the only kind of matrices that we consider for our group. There is an identity element, like I said, the identity matrix. Since they are invertible, they have a non-zero determinant. There is an inverse, and in general, matrix multiplication is associative, but always need not be commutative, right? And when you group all of these together, this particular group is called a general linear group. Let me switch back to red. This is called a general linear group. Because it's very generalized, there's nothing happening here. The only binary operation you have is matrix multiplication, and there's nothing else happening, right? So GL, so the N here represents the dimensions of the matrix of, let's say, some matrix M. So that means it's an N cross N matrix. All of these are square matrices. You can only find determinant for square matrices. So by default, our matrix group consists only of square matrices of order n, or of dimensions n cross n, and they're defined over the real numbers. So this implies real numbers. Now you might say, if we're generalizing it, why not generalize over anything? And you can generalize it to any field f, right? Which can also include your complex numbers, and then you can just simplify your notation. From here is where we derive all our specific cases of SO, special, orthogonal, unitary, so on and so forth. All of them are subsets of the general linear group. They're just parts, smaller parts of the general linear group. So yeah, a subset of a group would also be a group, and it's called a subgroup. Like how you have a subset, you have a subgroup. The subset, which is a group itself, is a subgroup. And a subgroup of that is called just linear groups. It's no longer general, it's just linear group. Now, using that, you can define again a special linear group. There's something special about this. So it's a subgroup of the general linear group of the bigger set of matrices, but the determinant is always set to 1. So you have some matrix G, I'll just call it G, for example. You have some matrix that goes A, B, C, D. So this is going to be G2 or GL2. Let me make sure the notations are correct. So this is going to be GL2 defined over some field F, right? So there's that. Now what SL2, so we have the determinant of this. GL2 is just going to be AD minus BC. And for the general linear group, we just say this is not equal to 0. Okay, but for the special linear group, if I was to consider the same matrix A, B, C, D, the determinant of SL2 will be equal to AD minus BC. The way you define it is still the same, but that is set to 1. That's what special. That's the special thing about the special linear groups. And using definitions like this is how you can define your other types of groups that are important to us. This is a section that I'll probably skip for now. It's not as important. If time permits, we can always come back to this and just revisit as to what Lie groups are and what Lie algebra is. In brief, a Lie group is more like, it's defined over something called a vector space, and this space you can differentiate. You can perform differential calculus on it. That's like the simplest way that I can tell you about this. And you have different kinds. You have discrete groups, continuous groups, and so on. A lot of technical jargon there, but all that you need to worry about is what kind of matrices are these. And one thing that turns out to be good is our general linear group that we have here, GL2, defined over the real space R, is also a Lie group. It satisfies all the conditions for it to be a Lie group. And fortunately, all the groups that we consider in physics that you may have seen, U1, SUN, SON, ON, and so on, all of them are also Lie groups. So that's like a good thing that happens to us. And it's using that is how you find out how many bosons are there for a given gauge field, and why do you have exactly 8 gluons in the standard model, and why do you exactly have 4 bosons, the W plus minus Z and the photon, right? It's using this Lie group and the Lie algebra that comes next that tell you about why exactly are those numbers there, why 8 and why not 9 and so on. Right, and so yeah, the Lie groups have Lie algebra, and it's these Lie algebras that tell us about the symmetries of the system that we're considering, the gauge field or whatever symmetries you consider in your quantum field theory and so on. Right, and one example of that is the rotation field, where you can rotate it by some arbitrary vector n cap. This is a vector, or more of a unit vector, and this is just some angle, or you might even call it the phase. Sorry about the background noise. Someone seems to be very active on the bike today. This is all about Lie algebra. I won't be getting into all of this. I will pass this presentation on in Discord. So the ones who are interested can go through it in detail. All right. We've already studied Lie groups. It's just that we've never been told those are Lie groups. One of the best examples that all of us know is the vector cross product, right? If you have two vectors A and B, the cross product is sort of anti-commutative. A cross B will give you the negative of B cross A, and the generators, the things that generate your three-dimensional space, your Euclidean 3D space, are the unit vectors Ex, Ey, Ez, or you might know them as I cap, J cap, and K cap. They're all the same, right? It's just that no one's ever told you that these are Lie groups, right? And another example that we are going through right now are the groups of square matrices, the general linear group, where the commutative bracket defined as AB minus BA. The ones who've done quantum mechanics would have come across this already. Those again form a Lie group, and like I said, it's a general Lie group where the matrices are non-singular, which means their determinant is not equal to 0. So you can go ahead and find their inverses and so on. All right. Now let's get into what kind of groups do we use in physics, right? So this is still not a physics-based approach. I am still sticking to a linear algebraic approach, and I'll tell you what these groups are and what they do, but I will just show you or tell you briefly how they can be applied in physics. All right. So the first we're going to deal with is the orthogonal groups. Now the name orthogonal kind of suggests something to do with perpendicular or something. That's like the first thing that comes to mind when you hear the word orthogonal. And in a sense, yes, it does deal with that, but it also tells us about rotations. All right. So if I have, let's say, a 3D space, X, Y, and Z, you can just name it arbitrarily. And if I have a green vector like so, I'm just going to call it, I don't know, V vector. All right. Now, if I was to apply some matrix from this so-called orthogonal group, it is going to get rotated to some different angle. All right. That's one way to look at it. All right. The other way to look at it is something a bit more bizarre, and I'm going to draw it down again. So we have X, we have Y, and we have Z, and we have our initial green vector, V, like so. I'm sorry, the color I think is a little light, but I hope you can still make out what's going on. Right, so what orthogonal groups do is they rotate either your vector or your space, but we physics people would like to, I think even the math people prefer rotating the entire space instead of rotating the vector itself. So what essentially happens is here at the top, we had the vector rotated to V dash, right? That was our rotated vector. But what happens here is the entire frame itself is rotated. So we have X prime. Oh, I think the color is really bad. You see, I think I'll probably just stick to red itself, but I'll probably put dashed lines. So the entire space is rotated, but the vector remains where it is. Now, what actually happens is the way you define your vector changes, right? So if you have, let's say, I cap, J cap, and K cap in your original system, after rotation, right, you have, let's say, I dash, J dash, and k dash, right? So if your vector was xi plus yj plus zk, then after rotation, it becomes v prime defined as some x prime, I prime, the whole coordinate system changes. So the way you define it changes, plus y prime, j prime, plus z prime, k prime, right? Uh, so what is happening here is a transformation. This is what linear transformation is sort of doing. But what's special about orthogonal transformation is, we had I perpendicular to j, perpendicular to k. After this transformation, it ensures that my I prime is still perpendicular to j prime, and that is still perpendicular to k prime. So, sorry, this is not right. So the perpendicular, the so-called orthogonality, or the fact that they remain perpendicular, is preserved. That's conserved, right? That's what's happening. And those a set of all matrices which do this kind of a transformation, which rotate by preserving the 90-degree angle between all of the coordinate axes, those are called the orthogonal matrices, and or the rotation matrices. If you're familiar with the rotation matrix, Rx, Ry, Rz, which are 3x3 matrices, it's the same, right? And a group of all of them, a set of all of them, defined over again matrix multiplication, is the set of orthogonal matrices, or the group of orthogonal matrices, called the orthogonal group, O of n. O stands for orthogonal, and n stands for the number of dimensions you have. So here it would have been O of 3. This again was O of 3. But you can go ahead and do it in 2 dimensions, you can do it in 4 dimensions, you can do it in n number of dimensions, right? And it will ensure that all your basis vectors, the I, j, k, in how many ever dimensions you have, remain perpendicular throughout. Now, a subgroup of this, where you specify that the determinant is equal to 1, the det q, the q is a matrix of the orthogonal group. If you set the determinant equal to +1, positive value, that's the special orthogonal group. It's special because all the matrices that are part of the special orthogonal group have a determinant equal to +1. That's it. There's nothing really crazy that's going on there. The subgroup SON is just the set of the group of all matrices where the determinant is equal to +1. That's it. So that's what I've defined here. It's a subgroup. This is how you define, this is how you denote a subgroup. So my special orthogonal group is a subgroup of the orthogonal group, the bigger orthogonal group, and they preserve the orientation, implies the perpendicularity of your basis vectors. And you're already familiar with all of those. SO2, SO3 are what you're familiar with. I'll just give you a quick example. Your R2 or your SO2 is cos theta sine theta minus sine theta cos theta. This is the 2-dimensional rotational matrix. So you can observe that the determinant, which is cos square theta plus sine square theta, is still equal to +1. And this represents a rotation by some angle theta in your 2-dimensional space. You can go ahead and build up a 3-dimensional case for the same. And that is why the group of orthogonal matrices, or special orthogonal matrices, are the rotational groups. And that's about the orthogonal groups. The next, we'll look at unitary. So what we've done here so far in the orthogonal groups is everything here depends on, is all real numbers. They're all real numbers. So definition, this is only for real numbers. Now, but we know that, if you've done a little bit of quantum mechanics, or if you've seen pop science videos, you know that our entire universe is quantum mechanical in nature, right? And quantum mechanics also has complex numbers that come in it, the factor of I, the square root of -1. So we have to sort of generalize this whole idea of orthogonal groups to the complex numbers or the complex space, and those are called the unitary groups. All right. So a unitary group is nothing but a set of matrices where all of them are unitary in nature. And what exactly do we mean by a unitary matrix is defined here. You have a matrix U as alpha, beta, gamma, delta, where all of them are complex numbers, right? So you can write all of them, alpha, beta, gamma, and delta. All of them can be written in the form A plus IB, where I is the square root of -1. And so when you do this, the concept of transpose isn't enough anymore. So you perform the dagger operation right here. And this implies the conjugate complex conjugate, and a transpose. So that's about Hermitian matrices, which we discussed in the beginning of the talk. So a set of all such matrices, all such unitary matrices, is the unitary group UN. Again, the binary operation is by default implied to be matrix multiplication, because all of these are subsets of the general linear group, the general group of matrices where the initial binary operation we defined was matrix multiplication. Right. So the unitary group is U of n, where n again is the dimension of the matrix that you have. So this will be a U of 2. This is basically U of 2 because it's a two-dimensional thing. It's a matrix of the order 2 cross 2. Now, unitary groups or the unitary matrices are what are used in Hilbert space that you might have heard about in quantum mechanics. Quantum mechanics is based completely on Hilbert space. Now, Hilbert space has its own definition, but we won't be getting into that. But why exactly does Hilbert space require unitary matrices or the unitary group is because it preserves the inner product. And by that, what I mean to tell is the group U of n doesn't change the distance between 2 points, right? I'm sure all of you just know how to measure distance in a 2D space. If you have 2 points x1, y1, and you have x2, y2, the distance, we call it d, is x2 minus x1 the whole square plus y2 minus y1 the whole square, and that's the square root. So if you when you try to generalize this, you can express this in the form of an inner product. And what unitary group does, or what the Hilbert space again by extension does, is it makes sure that this D remains the same no matter what you do on it. This D remains the same. What kind of transformation you do, whatever you do, the distance remains a constant. So that's about the unitary group. And again, when you take so you can go about how many parameters that does this unitary group depend on and so on. I won't be getting into that. You can just read this presentation once I send it to you. And since it's also being recorded and live streamed on YouTube, you can just pause it and have a read as to what's happening. All right. Now, again, like we did for orthogonal groups, we took a subset or a subgroup, SO. So I'll just write it here, orthogonal was O of n. You take a subgroup SO of n such that the determinant was equal to +1. You do the same thing for the unitary group as well. You have unitary group U of n. You take a subgroup of that, which is called SU of n, the special unitary group. The S just stands for special, such that the determinant again is equal to +1. That's it. That's your special unitary group. I mean, if you thought that this was too complicated groups and stuff, it isn't. It's just this, right? It's just a set of matrices with complex numbers as its entries, as you can see. Alpha, beta are complex numbers. I should probably mention that alpha and beta belong to the complex space. Right? They're just complex numbers. It's just a set of complex numbers or matrices with complex elements which have a determinant equal to +1. That's it. There's nothing more to special unitary groups as far as we are concerned right now. Okay. And that brings us to the end of unitary groups as well. And I hope it wasn't too complicated so far. Because what we're going to do now is we're going to look at an application of these unitary groups in quantum mechanics directly. All right. So yeah, we're going to learn about unitary operators. So matrices can also be called operators thanks to how we understand linear transformation. So if I just go back here, this can be called the rotation operator in 2 dimension. Right, because it operates on something, it does something to change it to something else. Right. So this is a rotation operator because it operates on what we call a vector, which we defined as a column matrix, and it in turn gives you some other vector. That's basically all this. That's what this is about, right? So any matrix you have, because of linear transformations, properties, and so on, it's fair enough that we call them operators. So any operator that you have is a matrix. It can be represented as a matrix. So the Hamiltonian, if you've heard about it, can also be represented as a matrix, and so on. So I won't be getting into the details of all of that. But the case we study here in quantum mechanics is to understand the time evolution of a system that you have. There's a lot of mathematics that goes on here. I won't be getting into the details of this. But what's happening, the main principle that we're worried about is the evolution of state vectors, the vectors that define my quantum mechanical system, that define the state of the system. That's why state vectors. How it evolves with time is unitary in nature. Right? And what we mean by that is the whole inner space thing is conserved, the distance is conserved, and it's on a Hilbert space, and so on and so forth. Right? Everything that we've studied so far is sort of preserved here. Right? So the entire quantum mechanical thing is preserved in our Hilbert space and is embedded with unitary matrices and so on. We make a few assumptions to go about all of this. It's just that, at time t equal to 0, we just assume that we know everything about the system at the initial state and so on. You can keep working it out. But one of the most important results is this. You can define your unitary operator to be like so, where you have the one is the identity matrix minus I epsilon h, where h is some operator, any operator. You don't know what it is, right? It can be any kind of an operator, but when you perform, when you make sure that it remains unitary throughout, you come at a astounding discovery or some astounding fact that whatever operator you take here in this definition has to be Hermitian always, right? And this is why there is a condition in quantum mechanics that no matter what operator you choose, it always must be Hermitian, because the fact that the entire thing is embedded in unitary groups and Hilbert space, it has to make sure that whatever operator you choose on this space has to be Hermitian in nature. So your Hamiltonian is Hermitian in nature. Your momentum operator is Hermitian in nature. Your position operator, your angular momentum, everything, your spin, everything is Hermitian in nature. And this is what we make use in tomorrow when we will discuss about symmetries and invariances and so on. All right. You can just keep going, and when you take a derivative, since we're trying to understand the time evolution, you stumble upon something that you didn't expect to find here at all. This is the Schrodinger equation, the time-dependent Schrodinger equation, and we weren't even looking for it. I mean, we didn't want to understand. I mean, we didn't want to derive Schrodinger's equation, but we still get it, right? And you can just call the edge to be a Hamiltonian for assumption purposes. And when you do that, you do get your Schrodinger equation, and that's like, I don't know, something mind-boggling when I first read about this, right? This is something that comes out of just the fact that you've assumed, or you're telling, that whatever happens in quantum mechanics is unitary in nature, right? And it's just that principle that led us to Schrodinger equation, the time-dependent Schrodinger equation. You can go back and read about all of this later on. It's a really fun concept to read about. Okay, I feel like I'm rushing a bit too much, but we're almost at the end of the talk. So, I'll probably slow down a little bit here. For the people who are below 11th grade, this might be a little complicated, but you don't have to worry. And for the people above that, 11th and so on, what we're going to talk about next is just product of sets, right? You're already familiar with how to multiply two sets. It's called the Cartesian product, right? So if I had, let's say, A equals to some A comma B, and I had B equal to some C, then the Cartesian product A cross B is defined as the ordered pair A comma C and B comma C, right? That's the Cartesian product. If you're not familiar with this, it's totally all right. It's just that you're multiplying two sets with different dimensions and so on. So when you try to extend that, when you give each of these set a binary operation, they become a group. So instead of A and B, I give them each a binary operation, and I call them groups, right? So you can call this to be A, this as B. It doesn't really make a difference. It's just two groups, and you multiply them. So you have two things here. You have two sets, G and H, and you have two binary operations, star and delta, right? And you know how to multiply sets. It's just a regular Cartesian product, which I've defined over here. That's fairly simple. And how you find the resultant binary operation is you perform it element wise. You see each element, which is an ordered pair, and then you work with it another ordered pair, and you you give them the same binary operations from where they belong. So I have G1, G2 from the group G, H1, H2 from the group H. So the final resultant binary operation is just going to be G1 star G2, which is the binary operation of G. So this is of G. And H1 delta H2, and this is the binary operation of H. It's nothing really, it's just an abstract concept. You don't really have to worry about all of this. But the reason I introduced this is because if you look at standard model, right, it has these three, SU3 cross SU2 cross U1. And this entire slide is just to explain what this cross is all about. It's called a direct product. There's, of course, this is the symmetry that the standard model has, but that's a thing for some other time. But this slide is is meant to explain what this cross is all about. All right. So there's that, and you can call this resultant thing G cross H, your direct product, whatever the result is, that you can verify that it's also a group, which I've verified here. The binary operation, both are associative, so the resultant is still associative. The direct product, there is an identity in both of them. So if you take both together, then you have an ordered pair 1, 1. That's also an identity, and this inverse for both of them because both of them are groups in themselves. And you can verify that this thing is a group in itself, and so on. All right. So that brings us to our last topic, and I think I do have a little bit more time. I have roughly 10 to 15 minutes. Okay, I think we can do this. All right, I won't be getting into the entire details of all of this, but we consider two groups, SO3 here and SU2. And it turns out that there is a really special relationship between both of them. Now, why do we have to bother ourselves with this? Is because SO3 is 3D real rotations, right? Our orthogonal groups were made of real numbers. So this and 3 represents 3 cross 3 matrices. So what SO3 represents is the group of all 3D real numbered rotational matrices. But SU2 is a 2D complex rotation, right? And what I mean by this is what does complex rotation actually mean is, if you have a Argand plane, a complex plane like this, where you have the real axis here and the imaginary axis here, and you have a complex number which can be represented like so. When you apply an SU2 transformation on that, because it's an operator, right? Every matrix is an operator. So any matrix from the SU2 is also an operator. And what that does to this vector is it rotates it, like in the blue one, like so, by an angle theta. So in a sense, you can already make out that there is a factor of e power I theta which works to rotate my vector, right? This is the SU2 operation. This is what SU2 does, right? That's the function. That's the whole way that SU2 group works. It rotates your complex numbers by a factor of e power I theta and so on, right? So now what we're telling is that there is some relation between these two. These two are somewhat related, right? And you can go through this entire presentation again. You consider unitary matrices and since we are dealing with physics, so and even general unitary matrices can be generated, or you can produce the entire set of unitary matrices using the Pauli spin matrices, which you may or may not have heard of. That's okay, it's totally fine. It's just a set of 2 cross 2 matrices. There's just 3 of them, sigma 1, sigma 2, and sigma 3. What happens is you can generate your entire unitary space with just these 3. Right? So they're called the generators. You can, like how you have ijk to define your entire 3D Euclidean space, you have sigma 1, sigma 2, sigma 3 for your unitary space. And you can relate that with the angular momentum, so on and so forth, a lot of mathematics. And what you end up with is something called a homomorphism. You find out, so I won't even get into details of what exactly a homomorphism is, but what I will tell you is, if I have, let's say, one second. Yeah. So, if I have, let's say, two circles here, okay, two, whatever it is, okay, and I have some element I2 and minus I2, okay, it's just, the dimension, the identity matrices, and this would be my SU2 group, okay, and here I have SO3, and I will just consider some random matrix. I'll call it Q. Okay. Now, the relation between these two turns out to be that it's this mapping, right? You can either call it like this or like this. It doesn't matter. The direction really doesn't matter. But what it is telling you is that for every element of SO3, for one orthogonal matrix of 3 dimensions, there are corresponding 2 unitary matrices that differ in sign. All right, and we will again get back to this tomorrow also when we're learning about symmetries. But this was one of the profound facts, something that was very I don't know, mind-opening, mind-boggling discovery, that there exists some correspondence between the SU2, which is a group of 2 cross 2 unitary matrices with determinant equal to +1, and the correspondence with SO3, which is a group of 3 cross 3 orthogonal rotation matrices with determinant equal to +1. The only thing that you can directly see what they have in common is the fact that they both have determinant equal to 1. Everything else is different about them. SO3 has real entries, SU2 has complex entries, SO3 is 3-dimensional, SU2 is 2-dimensional, right? And there is absolutely no way that you might have thought initially that there exists some relation between them, but it turns out that there is, right? And these I1, I2, and minus I2 are just identity elements which by themselves form group, and so on and so forth. And because of that, you have to sort of divide by another group called the quotient, called the integer group modulo 2. You don't have to worry about all of that, but this is the exact correspondence between SU2 and SO3, right? SU2 is isomorphic to SO3. Again, isomorphism is a concept that comes after homomorphism. I won't be getting into the details of that. But what are the consequences of this, right? Why are we worrying ourselves about what the relation of, why do we have to worry about this correspondence between SO3, SU2, and so on? Right. So the consequences of this is when you're studying the angular momentum operator J squared from quantum mechanics, you know that the spectrum of values, the range of values, can be given by J times J plus 1. H cross you can set equal to 1 in natural unit system, so you don't have to worry about that. But the range of J values ranges from the integer numbers 1, this should be 2 and this should be 3, sorry for the typo. And it can also be half integers. It can be half, 3 halves, 5 halves, 7 halves, and so on and so forth, right? And that itself tells you something about the particles that you already know, right? I'm a little skeptical about this point that I've written here, right? I'm not sure I understand it completely. But all in all, the summary of what SU3 and SU2 correspondence implies is you can differentiate between the types of particles that you have. Right, the entire set of particles that you have, we know that they can be divided as bosons and fermions. Bosons have integer spin and fermions have half integer spin. And you see, you are somewhat getting that, right? This is the angular momentum operator, but I think it's also the same with the spin operator. I just have to confirm that. I'll get back to you on that tomorrow. I think tomorrow I do cover about this. But yeah, what I need you to take away from this is just by understanding that there exists a correspondence between a unitary group and an orthogonal group of different dimensions, you can differentiate the whole type of the particles into 2 separate categories, the bosons and the fermions. And that's like, and then when you apply this idea to the spin statistics theorem, which is like a culmination of Bose-Einstein and Fermi-Dirac, you will find out that the bosons satisfy the Bose-Einstein statistics, the fermions satisfy the Fermi-Dirac statistics, and that's why they have half integer spin and so on. But in a sense, in the larger picture, in the very general terms, the reason why bosons and fermions have full integer and half integer spin has to do with these unitary groups and orthogonal groups. And that again comes from the fact, why exactly do bosons and fermions, or the particles as a whole, or the fields of particles, or why quantum field theory depends on SU2, SO3, U1, and SU3. is our concept for tomorrow. And with that, I conclude my talk. So for the reading, you can go back and read about actual group theory, Lie groups and Lie algebra, parameter spaces, representation theory of groups, and in detail about special linear groups and so on. These are long concepts, so you can't finish them in a single day. That's impossible. But yeah, this is something that is also taught at the undergrad level. Most of them, the rings, fields, vector spaces. The vector spaces are where your Lie algebra and all is defined. The Hilbert space is a vector space and so on. Right? Your topological spaces where you define your further things. I won't get into that. And again, in group theory, you have a lot of things. You have homomorphism, you have finite groups, discrete groups, and continuous groups, Lie groups, like we discussed a little bit, and then completely algebraic groups, nothing to do with physics or in a sense, right? And so on. So these are topics for further reading, and these are my references. And with that, I conclude my today's talk. Thank you very much for your patience. And assuming we have roughly 10, I have another 10 minutes, so I can take maybe 2-3 questions.
Vikrant, we have some questions in chat box.
All right, I'll just go through that. So Aryan has a question. Groups are also sets. Yes, groups are also sets, but they have an additional binary operation defined on them. So sets plus binary operations equals groups. So that's that. Okay, every group has sets with binary. Det Q equals -1. It just implies that the determinant of our orthogonal matrix is -1. It's of no use for us. It's not like we care about it, but they just exist, so it's fine. Okay. Sonal has a question. When you mentioned distance is preserved on application of unitary operation, did you mean the distance between 2 points remains same if unitary operation is applied to both the points? Okay, so what I mean by distance being preserved, the example that I gave you during the talk is it's like a very boiled down version of what distance actually is. But if I was to tell you in a crude sense, yes, right? Yeah, you can say that if you were to apply unitary operation to both the points, which actually you cannot, because it doesn't make sense to apply unitary operation on a point. Unitary by itself implies some matrix operation, and you can't do it for a point, but you can do it for a vector, right? And each point can be represented as a vector. So to the point directly, no. To the vector that corresponds to the point, yes. I hope that makes it clear. Sonal, do you mind unmuting and just letting me know if you have? Okay, thank you. Okay, Aryan has another question. Does only real number are also only real numbers are considered in unitary operators? No, unitary matrices or unitary operators are made up of complex numbers, right? So they are complex numbers, and you need that generalization. If you were to consider only real numbers, then you already have orthogonal groups. You already have orthogonal operators, rotation operators. So you don't have to worry about that. But the fact that our universe is quantum mechanical, every space that you talk about, every field that you talk about is complex in nature. So you deal more with unitary operators which have complex entries built in them, instead of dealing with orthogonal matrices which have real numbers, and then you convert that to something complex, right? And that's another place where this correspondence helps, right? So this correspondence, SO3 and SU2, sort of gives us that relation that, if you have something in real space, which is the orthogonal space, you can convert it in a way to the unitary space, right? You lose one dimension, but whatever that is, you can work on them like that. So, yeah. All right. If there's any other questions, I'd be happy to take them. All right. So I'm assuming there's no other questions. I do understand that this might have been a little too complicated for most of you, but that's okay. All right. I've tried to make it as simple as possible, but if you still do have questions, please do reach out to me on Discord. And I've also given my email address, so you can send me an email anytime, and I will get back to you as soon as I can. So my email address is here. I'm going to put that in red. I hope my screen is still shared. Yeah. You can reach out to me. I'll also leave it on the chat box, perhaps, so that you guys can just make a note of it. Yeah. So if everything's done and if there's no questions, then thank you for attending. And I will see you all tomorrow, where we discuss symmetries and a little bit about gauge theories. We'll have an introduction to what gauge theories are, but we will mostly focus on symmetries that are observed in the standard model, namely the U1, the SU2, and the SU3. We will have a look at those tomorrow.
Thank you so much, Vikrant. You really explained it really well and in a simplified manner. We were all able to understand. So I hope the math is not so intimidating for everyone after today's session. Yeah, looking forward to the next 2 days session. People here from the particle physics group, theory 2 and experimental, please take the time to go to Discord and have a meeting with people in your respective cohorts. You can get introduced or directly dive into your problem statements. Rest of you are going to be part of today's EM discussion happening from 8 o'clock. So we will see you in about 5 minutes if you're here. We're going to be meeting on Discord. You can leave the Zoom call now. Thank you. Once again, wonderful job, Vikrant.
Thank you very much. Thank you for everyone's patience. I'll also be taking the leave now. I have some other work to attend to.
Cool. See you. Bye.
See you. Bye-bye. Thank you all. Bye-bye.